Welcome to a rather lengthy discussion of graphs of equations. If there's a particular topic you want to refresh your memory on, just fast forward till you see this slide in the video, and when we are discussing that particular topic, it will be highlighted. So let's start with some definitions about plotting points in the Cartesian plane. You'll hear them called an ordered pair. And ordered pair just means that the numbers have to be in order. You want to put x first and then y. So the negative 3, 1 just means x equals negative 3 and y equals 1. So that tells us that this is not the same thing, right, as 1 comma negative 3, because now all of a sudden x equals 1 and y equals negative 3. So it's very important to realize that order matters in an ordered pair. Also, when we're dealing with the Cartesian plane, it's good to know the quadrants start here in the upper right hand corner and go counterclockwise around in this direction. So this is quadrant 1, 2, 3, and 4. If you want to memorize, in this quadrant both numbers x and y are positive, and down here they're both negative, that's fine, but you really don't need to memorize it. It'll just come as you work with it. You'll figure it out. Right? Positive things on the number line are in that direction, and then positive things are up in the y direction. The notation PAB just designates the point AB, right? And then the ordered pair AB itself just designates the graph of it. So again, more vocabulary. Here are some examples of points on the Cartesian plane, or sometimes called the coordinate plane. A here, right, is over 3 and up 1, so that's this point here. You can look through the rest of them, right? C is over 3, down 4, right, negative, negative, so that's why they're both negative, etc., etc. Here's an example where we're looking at smoking rates, right, percent of adult smokers. And they want us to plot these points on a graph where x is year and y is percent. So these don't always have to be normal numbers. So here's that graph, x starting basically at 2002 and moving on. You'll notice these little symbols here are just telling you that the axes don't start at 0, right? It starts and then there's a gap. So we know that on a normal xy axis plane, this would be 0 here. But obviously this distance from 0 to 2002 is not the same as from 2002 to 2003. So there's a gap, there's a break in it, and that just means there's a break in this. And same thing here. This distance from there to there can't be 18 if that is a distance of 1, so there's a break. All they've done is they've zoomed in the graph to show you what's happening for those years. Okay, moving on to finding the distance between 2 points. Good old Pythagoras gets us going with that idea, because any 2 points on the Cartesian plane will always have a horizontal difference and a vertical difference in their 2 points. So this picture here is just showing that if this was one point and this was another on the Cartesian plane, and we're trying to find this distance C, well, if we know the distance A and we know the distance B, with Pythagoras we know that a squared plus b squared equals c squared. And that's where this ugly formula comes from. Because if we have our coordinate plane and we have a point here and here, and this is going to be x1 and this is going to be x2, right? The locations. And then we come over here, this is going to be y1, that's going to be y2. Then hopefully you can see now that this distance from there to there is this distance here, which is just y1 minus y2. And then the horizontal distance here in green is this distance there, which is x2 minus x1. Now, you're thinking, well, you've got a 1 and a 2 and a 2 and a 1. It doesn't really matter in which direction. This is just your change in y, sometimes called delta y, and this is just going to be called your delta x. And it doesn't matter if you do x2 minus x1 or x1 minus x2, because according to Pythagoras we have to square them, right? And if you do it in the opposite direction, you're just going to get the same number but a negative. So if you did, let's say, x2 minus x1, in this case you'd get a positive number, because we know this number is going to be bigger than that one because it's further to the right. So if this was 10 and this was 3, then we would get a 7. But if you did x1 minus x2, you would just get negative 7. But when you square it, it's still going to be 49 both ways. So that's why it doesn't matter which one comes first. You're just looking at your change in x and your change in y, and then you're squaring them. Well, this is my a, this is my b, and we're looking for c, right? So this ends up being, if we want to write it over here, a squared plus b squared square rooted, and we know that a squared plus b squared equals c squared. So if we want to solve for c, all we do is take the square root of both sides, which equals c, and that's what the distance formula is. It's really just Pythagoras' theorem in disguise. Don't let all the x sub 2's and x sub 1's and all that stuff confuse you. Every time you want to find the distance between 2 points, just kind of give yourself a basic picture and find these distances, b's and a's, as just your change in y and your change in x. Square them, add them together, take the square root, and you're doing Pythagoras' theorem. Here's their picture where they're talking about the absolute values, right? Here's an example where they're actually plugging in some numbers. You can work through the numbers and see how it works. If we were to graph these 2 points on a number line, on a Cartesian plane, -2, +5 up here, +3, -4 somewhere down there. Here's the distance we're trying to find, right? This is my c. So you think about, I'm just going to draw in this right triangle. And if this is a -2, 5, and this is a 3, -4, then this point here, we know from there to there, is going from -2 to 3. So that's a distance of 5. And if I'm going from here up to there, well, that's -4 up to 5, which is a distance of 9. And so I know by Pythagoras' theorem, 5 squared plus 9 squared equals c squared. And so to solve for c, I take the square root of both of them, and look at this. That's that step right there. So with a little picture and a little logic, you can bypass having to use this ugly formula. Finding the midpoint. Well, the midpoint formula is actually a lot simpler than it looks. Again, another ugly formula, but this is what's happening. You've got this idea of, well, I know that the overall distance from P to Q in the horizontal is going to be my change in x, right? That's how much x is changing. And I know this distance here is going to be my change in y. Well, the midpoint of that line is just going to have half the horizontal change and half the vertical change. This right here is exactly half. This right here is exactly half. So all they're doing is taking the midpoint of each of those distances, horizontal and vertical. And the midpoint of any 2 points is their average. I know you might be saying, why is it the average? Well, this point here, let's put some numbers in here. Let's call this 3, comma 3. So it's over 3 up 3. And this is going to be, how about 13, comma 3. And so this one's going to be 13, comma, how about 9. So what's our delta x, right? What's the distance between this point and this point? Well, it's from going from 3, 3 to 13, 3. So we have an x of 3 here, right? This is at 3. This one's at 13. So isn't that a distance of 10? And wouldn't half of that distance be 5? And we would add it to the lower one. And so we know this is at 8. Well, from the origin all the way to 13, that's a distance of 13, duh, right? And then from 0 to 3, here to here, that's a distance of 3. If we take, we'll do it in different colors. If we take this whole distance to 13, add this distance to it, and then divide by 2, we're taking the average of those two distances, and that gives us the midpoint. If you do the math, you'll see 13 plus 3, 16. 16 divided by 2 is 8. Same thing's going to happen in the vertical distance. So this midpoint formula is just finding the midpoint of each of your x distances and your y distances. So really you're just finding the average of two numbers. What's the average of my x's? What's the average of my y's? That's going to be the midpoint. Here's an example with some numbers. A little more vocabulary we have to worry about just so we're all on the same page. We say that an ordered pair satisfies an equation if, when we plug in those two values for x and y, they actually make the equation true. Seems kind of obvious. What does that mean? Y equals 3x plus 5. Hopefully you know that if we graph that, that's going to be a straight line. And a straight line has infinitely many points on it. So there are going to be a lot of ordered pairs A, B that would satisfy this equation. One very simple one would be, how about 0, comma 5? Is 0, 5 a solution of that equation? Well, if you plug in 0 for x, you see that you get y equals 5, and 0, 5 works. Okay? What about 1, comma 5? Does that one work? And you see that when you plug in 1 for x, you get 8 for y, and this one is not a solution. You'll also notice that when I was checking these, I was plugging in for x first and then figuring out what y was. And that's because when we have something written in this form, x is considered our independent variable and y is considered our dependent variable, because the things are happening to x, right? X gets multiplied by 3 and then you add 5 to it and then the answer is y, which brings us to our next two, independent and dependent. Okay, so when they talk about independent variables and dependent variables, the independent variable is just the input and the dependent variable is the output. And anytime you have something written in the form y equals a bunch of stuff, whatever variables are over here on the right hand side, that's going to be your independent variable and this is going to be your dependent variable. If you had, x equals 3y plus 10, you would probably consider y to be independent and x to be dependent because of the way it's written. Now for our purposes, whenever we're talking about the Cartesian plane, we're always going to let x be our independent, our input, and then y is going to be the dependent. So even if we had something written like this, we would solve for y. we would have x minus 10 equals 3y. Then we would divide both sides by 3, and we would finally say y equals 1/3 x minus 10/3, and it's back in kind of a standard form. So usually x is considered our independent and y is our dependent. It's not set in stone. It doesn't always have to be that way, but 99.9% of the examples we're going to see, that's what it's going to be. On to the next thing, sketching a graph by plotting some points. So a graph of an equation, right, by definition, is just any shape that describes all of the ordered pairs. Sometimes it's just a bunch of dots, sometimes it's a straight line, sometimes it's a curved line. It just depends on how many ordered pairs you have. Here's a simple example where we're trying to sketch the graph of y equals x squared minus 3. So all we do is take a bunch of values for x, because remember that's our independent variable. So we pick a bunch of almost seemingly random, but basically you start at 0 and kind of work out in both directions. Pick a bunch, plug them in, get a bunch of answers. There's all of our ordered pairs. And so when we plot all those ordered pairs, we then connect the dots. Now, unless you know something about what an x squared minus 3 function looks like, you might try to, I don't know, connect the dots, and I just cannot draw well. You might try to connect the dots. Let's get rid of this. Let's try that again. You might try to connect the dots with maybe a straight line. If I could draw a straight line, you'd understand it. But if you've dealt with squares, you know that they're parabolas, right? And parabolas are nice curvy things, up or down, wide, narrow, whatever. You know that they're of a certain shape. So that helps too. So just plotting points isn't good enough. You need to know a little bit about something. Here are your steps. Make a table, pick some values for x, stick them in the equation, get your answers for y, figure out all of your ordered pairs, plot them, connect the dots. It's just that simple. When we talk about an x-intercept and a y-intercept, those are just where the functions cross the x and y axes, right? So the x-intercept is where it intercepts or intersects, crosses the x-axis, and the y-intercept is where it crosses the y-axis. So up here on this picture, we have x-intercepts here at about, I don't know, negative 1.8 and positive 1.8, and then our y-intercept is down here at negative 3. Right? So when we're talking about where it crosses the x-axis, we give that answer in terms of x, and when we talk about where it crosses the y-axis, we give that answer in terms of y. Next, we talk about the intercepts of a graph. And to find them, it's a very easy process. If we want to find the x-intercepts, that's just where the function has a height of 0, so we set the height to be 0, so we set y to be 0. And if we're trying to find the y-intercepts, that's just where x equals 0. That's the easiest one to find, actually. Here's a simple example. Here's our function. What's it going to look like? Right now you're all screaming at me it's going to be a parabola, and how do we know it's going to be a parabola? Because it has that lovely x squared piece. So to find the intercepts, they start off with setting y equal to 0 and solving. That's the harder of the two, but we've done some work and we know how to solve quadratics. Set them equal to 0, the only thing we can do is factor them, find our two factors, set each of those equal to 0, right, and get our two intercepts. So it's going to cross when x equals minus 1 and positive 2. Second, we set x equal to 0, which is really simple. You just make all the x's 0 in your original equation, and you get y equals negative 2. So if we plotted those 3 points, there's the minus 1, there's the positive 2, There's the negative 2 for y, and then we would try and connect those dots. If you've worked a lot with quadratics, you kind of know their shape. You can kind of figure it out from just 3 of them. If not, just plot some more and connect those dots. Symmetry just means that something has a mirror image. If something is symmetrical, you can cut it in half and the two halves will look the same. Parabolas are usually symmetrical, right? A circle is symmetrical in all directions. A rectangle will be symmetrical in 2 directions. Now, don't laugh when I try and draw this, but all right, so here's a really crappy version of a rectangle. You get the idea. If I were to cut it in half, right down the middle this way, these two sides would look exactly the same. And if I cut it in half that way, those two sides would also look the same. Now what about a square? Again, no snickering. There's my square, not too bad. We can see that cut it this way, it's the same. Cut it that way, it's the same. But what about cutting it that way? Aha! Or cutting it that way, right? So some objects will have more symmetry than others. So to find the symmetries in a graph, all we have to do is look at it and go, duh, it looks pretty symmetrical. But algebraically what it means is every time we have a point xy, we know we have to have the opposite, negative xy, also in that graph. And that's if it's symmetrical to the y-axis. i.e. does it have vertical symmetry, right? If we draw a vertical line through it, is it going to be the same shape in both directions? And if it is, this will happen, right? Every time we have 3, 2, we have to have negative 3, 2 as well, etc., etc., etc. If we have horizontal symmetry, how do you think that's going to change? Well, it just means for every x, we now have a mirrored pair of y's. And that's because if you cut it in half with this axis, you get the mirror in both directions. Now remember, this is only symmetrical with respect to the x-axis. The previous one was the y-axis. This is the x-axis. What if you had, here are my axes, and I have a nice, pretty symmetrical parabola over here. So that's supposed to be symmetrical. Is it symmetrical with respect to the y-axis? And hopefully you're all saying no. And with the x-axis, also no. But is it symmetrical? Absolutely. But it's not symmetrical to either of the axes. It's symmetrical to, well, that's a bad line at the bottom, but you get the idea. That line there. Because now these distances are the same. Okay? Just like these two distances over here are the same. That's what those little lines mean, that those two things have the same distance. So symmetry doesn't have to be around the axes, but when it is around the axes, we get these nice special things where if it's symmetrical around the y-axis, we get this beautiful relationship where for every y, we get a pair of x's, plus and minus. And then when it's symmetrical around the x-axis, for every x, we get a pair of y's, plus and minus. We can also have what's called symmetrical with respect to the origin, and that just means every time we have an ordered pair, we have its opposite ordered pair. So for every xy, we get the negative x, negative y pair. And then you can see again this idea of distances. This distance is the same as this distance. And that comes right back from our distance formula. If we're going over x and up y, but now we're going over x and y in a negative direction, aren't these still the same distances, right? This is still, a negative distance is still the same distance as a positive distance if these two distances are the same. So if we go over 3 to the right versus over 3 to the left, it's still a distance of 3. If we go up 5 versus down 5, still the same distance. And so by Pythagorean's theorem, we know those two hypotenuses, right, of our right triangle are also going to be the same length, and therefore those 2 points are the exact same distances. Checking for symmetry, just to determine if something is symmetrical, is just plugging in, right? Because we know that if it's symmetrical in one direction, we're going to have a pair of x's, right? If it's symmetrical in the other direction, we know we're going to have a pair of y's, and if it's symmetrical across the origin, we know that both are going to work. So it's just a matter of checking. We can see in this first example that if I plug in a negative value for x, I will always get the exact same thing as if I plug in a positive value for x, because you're squaring things. So which symmetry is it going to be? Well, it's not that one, right? Because if I plugged in a negative x, I'd also have to get a negative y, whereas here I get the same y. Okay, so what about this one? If I plug in a different x, nope, that's got different y's. How about this one? Different x's, same y? There it is. So that one's symmetrical with respect to the x-axis. Okay? Here's how you can work it out. You can replace each one to check it. Symmetry is not a real big, it's not a real important thing, guys. You can always just plot some points. So this is a lot of memorization, in my opinion, and it's really not worth the brain power. But if you want to work through these and get better at recognizing symmetries, by all means do so. It's not going to really hurt you if you don't. You can always just plot points, and then once you have a graph of it, you can kind of figure out from looking at it whether or not it's going to be symmetrical to the x-axis, symmetrical to the y-axis, or maybe symmetrical to the origin. Last but not least, looking at the equations of a circle, a very specialized graph. We all know what a circle is, so I'm not going to waste time talking about this. You know what the radius is. Right? Just know that when the book talks about a circle, the center is always at HK. So here is your generalized picture of a circle. There's your center, HK, where H is your horizontal, right, distance, K is your vertical. So it's really just your X and your Y. Why did they use HK? Just to confuse you guys. No, really, it's just because the center is kind of special, and so we give it a different set of letters. And then that way, when we talk about all of the points that make up the actual circle itself, we can reserve XY for those points. That's the only reason. Okay, here is the generalized equation for a circle. It's always x minus whatever the x coordinate of the center is, squared, right, plus y minus the y version of the center squared equals r squared. It looks very similar to a squared plus b squared equals c squared. Right? It's very similar to Pythagoras' theorem. So that might help you to memorize it a little bit. Here it is again, standard form. Here's an example. If they tell you what the center is, they tell you what the radius is. It's just a matter of plugging everything in. If you got to graph it, just plot some points. Or if they give it to you in standard form, you kind of know what's going on, right? This first one, there's no pluses and minuses, so that means it was zeros and zeros. So the center has to be at 0 and the radius has to be 1, and there is what is called the unit circle, which is what we're going to use a lot when we start talking about trig. For the second version, we can see that it's x plus 2 and y minus 3, and you have to remember, okay, what was the formula? Right? The formula is minus, right? X minus h, x and y minus k. So if this started off as x minus h, what does h equal? It equals negative 2. And here, k equals 3. So this circle would be to the left by 2, down by 3, and obviously a different scale. It would be 2, and it would be way over here, but you get the idea. Here's the picture of it. Sorry, I did that wrong. I went down 3 instead of up 3. So left 2, up 3. There's your circle. Radius of 5. And you just start plotting points from there. Wouldn't worry about it much, guys. Just kind of try to remember that it's x minus h and y minus k is going to be the most helpful part from that. The general form of equation, the general form of the equation of a circle is the same thing, just kind of everything's multiplied out and set equal to 0. Don't get bogged down with all these formulas. Okay, we've got technology that'll graph these things for us. Just be aware of where the x's and the y's are. That's all that matters.